Okay, so I need to go to this. Okay. Please mute your computer. Okay, so this is computational poromechanics class. Okay. So I haven't get the chance to teach this class for 3 years. I believe last year I was in sabbatical, which I was supposed to teach that course, but this is actually you want to take a look from this laptop? I mean, I have my phone. Oh, I mean, you're welcome. Yeah. Okay. Yeah. Okay. Yeah, you can both use that. Okay. And please mute the device so that I can. You can just. Okay. So let me explain what it is. So the study of computational mechanics or computational. We're almost there. Okay, next time we'll try to reserve the 7 for if we cannot get the same time slot, I'll try to see whether I can find another alternative time. I think that will make everyone easier. But I'll try to schedule so that everyone can do it. I think that yeah, okay. So luckily there is no COVID thing happening. Otherwise it would be really too dense. Okay, but okay, so let's get back to business. So the course is about computational poromechanics, and I think this is actually a generalized version of the computational mechanics. When people think that computational mechanics is more broad, but that's not true. Most of the material have some pores in it, which means that the voids, in particular in civil engineering. So let me explain the terminology. So there's a computations. I think it's pretty obvious using computer, and then there's a pore mechanics. So there's 2 words there. Pores refer to porous media. Okay, so what is a porous media? It's a material that actually have a solid phase, which means that the part of the area is volume is occupied by solid, and a part of it is actually occupied by fluid. Okay, so now you may wonder, I can have a hole. It doesn't necessarily fill with water, right? So why there's a fluid phase? Okay, but on Earth, I mean, we are not studying something in the in the outer space. The voids are still filled with air, so air is one kind of fluid. Now, more precisely, the poromechanics, porous media are filled with more than one fluid. Okay, so there's an S there, and they interact with each other. Okay, so you can imagine that if I imagine there's an orange, okay, and you try to squeezing it, there's a juice coming out. So you actually introduce a mechanical response, but then that mechanical response also trigger a hydraulic response. Okay, so you see what I mean? On the other hand, like there are other interactions that are actually using hydraulic part to trigger the mechanical response. One example is the hydraulic fracking. You inject enormous amount of white water until you build up at least enough pressure to introduce fracture to the material. After the material is fractured, it's much easier to extract oil. Okay, of course there are environmental consequences where would the water go, etc., etc. Okay, so the course will focus on how to learn the pore mechanics so that you can apply to a computer. Okay, is that clear? Okay, so far so good. So and the course is actually related to the course that you study in undergrad, soil mechanics. Okay, so how many of you have already taken the course soil mechanics? Okay, you all know what is a phase diagram. Okay, or okay, how to calculate your consolidation settlement. So okay, so hopefully, okay, we'll provide a more theoretical background on that. Okay, now go back to the pulse media. Can you guys name one pulse media that you encounter? Give me an example. Okay, okay, that's a beautiful material. Okay, so what other example? You have no ideas. Okay, so can you think of something that have water and solid and then they actually kind of hold together? Soil, okay, that's good. Soil, I mean, you can argue that clay is one kind of soil, but that's actually true. So how about
The orange example.
the orange? Okay, okay, that's pretty smart. I mean, most of the biological material are porous. I mean, not all. Well, I would say all of the biological material are porous media. Actually, most of them are saturated with fluid. That's why when you do a surgery, you also need combination mechanics to pore mechanics from the simulation. If you, how about you? Sponge. Oh, sponge. Okay. Almost anything. Okay, sponge would be a very specific type of porous media that have very lead to solid volume with a lot of voids, and that could lead to different characteristics. Very important material. None. Huh? Oh, the human lung. Okay, that's true. Just biological tissue. In fact, even bone is porous media. It's actually not saturated with water, but they're liquid inside the bone. Styrofoam. Okay, okay, okay. So I think that's true. And how about you? Sand. Okay. You were taking my facility class years ago. Okay, yes. So I never see the face, but I think, but I didn't remember. No, it's okay. Yeah, don't worry. Concrete. Yeah, concrete. Okay. I'm waiting for someone to say concrete because okay, concrete. Concrete is a porous media, and sometimes you wish it's not a porous media, but it is. So okay, for obvious reasons. Okay, so this is actually can give you an idea of how common the material is. Now, there are two approaches to modeling this material from a simulation perspective. Okay, obviously, one is that I can model each drop of liquid and each drop of solid and each piece of solid in great details. Okay, meshing it in finite element and identify this material one, material two, and liquid. Okay, so this is actually would be a way of modeling it. So, sorry, I will actually really go to the question very soon. Okay, so basically there are two approaches and they're related to scale. In small scale, okay, we can model directly the fluid-solid interactions. So what it means is that I would actually have a porous media with the solid, and then the water that are inside, I would actually explicitly model the motions. Okay, this is one explicit way to modeling it. Okay, what is the benefit of doing that? Is that it's actually really accurate. Okay, if you can match it properly and run the code. However, it's very difficult. Okay, so how many of you have taken the finite element course? Okay, so that's great. Okay, you can try to do it at home. Okay, imagine that you have a heat conduction problem, and then you actually have a K1, K1, K2, K2, and K1 is actually 10, and K2 is actually 1. Okay, what is the effective porous media of this material? Yeah, okay. So if you have this checkerboard pattern, okay, one is more permeable, 10 times more permeable than the other. Okay, use a different color. Okay, the red quartz is actually 10 times more porous than the purple blocks, and we organize it in a checkerboard way. So what is the effective porous media, effective conductivity? Huh? Okay, you kind of need to know how the water is moving. Okay, let's give another example. Okay, if this is actually arranging like this, so K equals to 10 here, K1 equals to 1, what would be the permeability? Versus if you actually, the water going through this way. Versus if you're going through this way. Okay, so let me ask one question. Is case 1 and case 2 has the same permeability? No, okay, you can think about a traffic jam that's like because George Washington Bridge. This one is like I just close one highway, another one is still working. Okay, so we'll be slow down. Okay, but I guess it's not as severe as this one on the one in the top where everything is broken. Right, does that make sense? Okay, what would be the exact number?
Case 1 would be 10. Because it has to go through the first one.
The first part is 10, but then the second one is slow down. So what would be that be?
It's 1.
It's also not 1, it's a little bit better than 1 because imagine that you're actually driving a car. Okay, the part of the highway that in normal speed, part of this is only 10 times as fast as before. It's still faster, right? Okay, but you have to go through the barrier. Okay, okay, you see what I mean? Okay. No. Okay. Okay, so if you go back to the solid mechanics class, there's an answer. I think the answer is, do you remember? It's K1 times K2 divided by K1 plus K2 or something like that. Sorry, okay, so maybe it's not. Anyway, I will actually provide an answer. One is for parallel, one is for. But why do I actually want to mention this first option is the following. Now, if you actually try to match a finite element, you would also not get the analytical solutions. Okay, so since you take the finite element, let me explain the mechanism a little bit. Imagine that I'm matching this. Let's look at one element. Okay, one element has 4 gaseous bonds typically if you want to do the full integrations. Okay, now the material behavior have a jump here, meaning that at this boundary, K is equals to 10, and at this boundary, K is only equal to 1. Okay, when you're solving it in a finite element, that's a gaseous bond. Okay, if I use one match, the gaseous bond is here, so I have 10, 10, 10, 10, 10, 10, 10 here, but I need to integrate this integral. So I would actually have an average values here, 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 and I would get my effective permeability that I calculate would be something like this. So this is not accepted. Okay, so if you want to model a two-phase material, one of the difficulty is actually to model to meshing it properly. Okay, so when you solve a boundary problem, if the material behavior changes smoothly, you can actually perform a good integration. Gaseous bond integrations, when you have a jump, it's not so simple. Okay, and calculating the integrations is necessary to compute the finite element calculations. Okay, so there's motivation one why this is actually hard, but somehow you have to do it. What is the second reason that we cannot do it? Is actually the following. Think about it from the perspective of the water. Okay, so let's say the water is yellow, so I'm just using this. Okay, now I actually deform this material. Okay, from a square to another shape. How do I? Sorry. Okay, this is good. Okay, so imagine that I have this porous media, and at time equals to at time equal to 0, the material is like this, and then there's a porous media. And then I'm going to deform the material by some kind of deformations. Okay, so that it actually becomes something like this. And then I keep track of the solid. Okay, I keep track of the 6 solid that are now moving from here to here. So what happened to the water? Okay, so the water, imagine that this is actually a free surface, so water can come in and out. So the water molecule that you keep track here is not the water molecule that you keep track here. Not all of them are there because the water can move out and move in, right? Okay, so from the perspective of the simulations, this also become hard because if you model finite elements, you want to have a fixed domain, but now the domain is also not fixed. Okay, so what is the possibility to overcome these issues? Okay, so there are one way. One is to keep track of the boundary using some kind of level set lead or another way is to model the liquid as some kind of imaginary particle and then allow the particle to move. And then I get the rough idea where water is going. Okay, the first one is called the level set method. The other one is actually called the material point method. Okay, does that make sense? Okay, now I just want to motivate you. I mean, you may find that this is actually a little bit wider, and this is okay because we are not going to cover that. This is actually why we do not do this way. Okay, what are the alternatives to model the porous media instead of explicitly model the boundary? Okay, another way is to imagining it as a mixture of material. Okay, what is the mixture? Okay, milk, for example, is a mixture, is homogenized. So what does the homogenized mean? Okay, if you see the raw milk, after a while it consolidates and you can see different layer. Some oil is on the top and then some solid. Okay, what does the homogenized mean? Is that you spin it and then you do some chemical thing until that whole liquid is actually have a same property in different space. Okay, this is the definitions of homogeneous. Okay, homogenized milk meaning that you won't encounter something thicker in the bottom and layer on the top. Okay, so another way to model the porous media is kind of like the milk. We actually did not explicitly model the solid and fluid, but we model it as some kind of mixture. Okay, does that make sense? Okay, so this is actually called mixture theory. And this is actually the focus of this course, which actually make it a little bit easier and connect to the solid mechanics. In fact, if you study the solid mechanics, you're also modeling as a mixture theory. You never explicitly model the liquid as an individual molecule or the solid as individual molecule. You model it as a mixture material. Okay, so far so good. Okay. Okay, so now we have the mixture. So we have that porous media as a mixture. So what should we do? Okay, so we would actually using another way to consider the material. Let's give x, y, z coordinate. I will call it x1, x2, x3. This is actually 3 axes. Okay, separate by 90 degrees. You've seen that before, right? Okay, so this is great. Okay, then I imagine that let's consider that there's a potato here. Okay, potato is also porous media. Okay, or actually any continuum basis. Okay, so let's consider one exact point. Okay, maybe not necessarily at the middle, just one arbitrary point here. Okay, so physically, if you point to one point and then that point is very, very sharp, what do you see? Okay, you will either see a solid or fluid. Okay, consider it as a two-phase material. Okay, so this point, can be either fluid or solid. Okay, it cannot be simultaneously fluid or solid, right? Right. Okay. But now let's do a trick here. I do not actually consider exactly a point, but I associate the point with a size. Okay, I was sampling it with a size that is called representative volumetric element or representative elementary volume. I'll spell it out later. Okay, in this size, okay, so if I associate the point with a size, so what would I see here? Okay, so now I will have a volume. Okay, so this one have a volume. Does that make sense? And in that volume, there could be a part of it that are actually solid. Does that make sense? And there's a part of it that is fluid. Okay, does that make sense? Okay, the larger I have, the less fluctuations I have, the smaller I have, I start to see the fluctuations. You see, do you also understand that part? Okay, so in reality, when you point something as hard as a needle, you will never encounter two materials occupy the same space. Okay. Okay. So, but in here, I'm actually weaken that point deformations. I'm assuming that each point is associated with finite size of sampling. Then I will have a volume. Okay. Now, if I actually consider this point occupying the entire space with a finite volume, then I would have a mixture. Okay, I'm assuming that at each of these points, which is not physically a point, but an RVU point, actually have a portion of it that are solid and a portion of it that are fluid. Okay. And now, then what should we do about it is that we actually need to zoom it in. Now I'm going to redo what we did, but instead I'll consider a bigger material and I'll part of it that are solid. Okay, and this is it. And then I would actually consider a very small volume. Okay, the DVS. This is actually occupied this is actually the solid, and then the empty space, which is actually the blue area, is actually DVF. Okay, so in the infinitesimal change, if I actually sample a very small area, but not smaller than the individual material point, I will have a DVF plus DVS plus DV. Okay, which is actually kind of like this, but then in an incremental form of it. Okay, so far so good. Okay. Now, the reason I put the D here, can anyone guess why?
It's very small.
Yeah, it's very small. And why do I need something very small? Is that I want to do calculus. Okay, okay. So we need to introducing the game of calculus in it, but you should see that in soil mechanics. Okay, I'm just defining it more rigorously in mathematical term. Now, okay. So from this view to this view, this one is called the microscopic scale. Okay, which we consider the individual water molecule, and this one is called the continuum scale or the microscopic scale. Okay, so all the post-media theory, geotechnical engineering theory are basically focused on the continuum scale. There are some exceptions, like a ladder Boltzmann coupled with finite element or whatever, and a multi-scale modeling that are actually into that regime. Now, if I actually want to introduce more terminology just for convenience, I may not actually want to directly with using the DVF and DVS all the time, the volume fractions. So what I can actually do is to introduce a concept called porosity. Okay, if you study the undergraduate soil mechanics, you probably know. And then we will call it theta F. Does that make sense? Okay. Now, but before that, I want to establish the connections between these two more formally. So let's consider the RVE questions. Okay. Okay. So there is an important concept representative of elementary volume. Okay. So now consider very small spaces, and then I would actually have this domain. Okay, and then I have some solid phase. And then this entire thing is just increment of dV. Okay. Now, what do I want to do is that I want to pinpoint it randomly into that space. Okay. And then I want to say that, and I want to introduce a concept called integrated functions. Okay. So okay, integrated function is a binary function, either 1 or 0. Okay, so if it's 1, it means something is true. Okay, so one of the integrated functions is actually x1 xs, which is actually we call it 1 if this position vector out is actually within the domain of dvs. Okay, does that make sense? Okay. Okay, so if I actually give, so this R is actually a position vector. Okay, is that okay? Now this actually equals to 0 otherwise, and there is no in between. Okay, it can either be solid. I mean, the material can either be solid or fluid, but not somewhere in between now. Okay. Now then, there's another counterpart that are actually opposite. Okay. So what they mean is that indicate it's actually a function that take a position vector and then return either 1 or 0. Okay. In the first case, it return the indicator function of the solid, and in the second case, it return the indications functions of the fluid. Okay. So far so good. Okay. Now I want to ask you a very important questions. What is the when you combine these values in any space in dV, what is the values without any additional information? Can it be 2? It's impossible to be 2, because if it's 2, then I'm saying that it can be both solid and fluid 100%, which is actually not possible. Okay, can it be 0? It cannot be 0, because you get there's either logical statement, so they always equal to 1. Okay, so far so good. It's actually very trivial, I guess, up to this point. Okay, now let me introduce more terminology. So, okay, let's consider this part, and let's consider this dV as something very small than dV. Okay, so this is an example of this anywhere. Okay, it's a dV. Okay, now the entire dVs, the solid, if I rewrite it as a function of the integrator function, is simply the integral of it along with the indicator functions, right? Does that make sense? Okay. And the same thing for use the same color. And the same thing for the tulip. Okay. So again, then we are again proving that this plus dVs equals to 1. Okay. So far so good. Okay, everyone follow. Now, if you actually start to loss what I'm talking about, feel free to stop me. I can explain it in another way. Okay, so far so good. You're still with me? Okay, so now before, I'm going to review some more concept in the undergraduate mechanics, and then I would actually go to the other part. Okay, so volume fractions. Okay, so I will introduce two terminology. One is the volume fraction of solid, which is actually dVs divided by dV. Okay, so it's telling you that how much of the portion of it is solid. Okay, which is actually simply this. Okay, this is pretty trivial, right? Isn't it? And then there's another one. And this one have a name called porosity. Okay. So porosity is actually something that are within the range of 0 and 1. Okay. What is the physical meaning of it being 0? No pores. Okay. Full solid. Okay. And like crystal, you can argue that a perfect crystal have no solid, no fluid, there's no hole there, no defects, no anything. It's just solid. It's just lattice. Okay, so what is the meaning of porosity equals to 1?
It's air, no material.
Yeah, no solid material. Okay, that could be matter, plasma, whatever. Okay, just no solid. Okay. Okay, so this is actually a quick review of the undergraduate course. Okay, now we want to introduce something a little more generalized. Okay. So if you work on a course, if you work on an oil company, which I'm not so sure nowadays, what is the Colombia policy on that? But sorry, I think I should not record this. But anyway, if you work in an oil company, you're not very likely never deal with that much two-phase porous media. Why is that? Okay, because they're oil and they are air and they are water, and there could be a phase transition. So what I'm talking about, the two-phase materials generalizations usually work in a very shallow ground. Okay, for geotechnical engineering, for example, you deal with the water table and then the dry zone. That two phase media is actually a good assumption. In general, we deal with a multi-phase system. Okay, so I need to generalize the concept that I provided before. Now I have an indicator function of alpha, and if I actually, which is actually equals to the volume of fractions of alpha phase, and that alpha phase could be anything. It could be solid, like what I said before, can be fluid, okay, can be plasma, can be two solid. Okay, if a frozen solid, we have two solid. For example, concrete, if you think about it very accurately, you have the host matrix and you have aggregate, you have multiple different solids. Okay, so now the same philosophy about what we did still apply, but we will actually have to introduce extra term and multiple integration functions, where the small volume is much smaller than macroscopic volume, and then there are volume fractions for the alpha term that are related to this. Okay, so now again, the total volume fractions, if I actually sum up everything together, it's actually equals to 1, where Kuiper is actually equals to the number of phases. Okay, so far so good. Now you may wonder, why do I care? Okay, so why don't everything just two phase? Okay, because most likely multiple phase material have different mechanism. For example, there's something called wettability. Okay, have you guys heard of what is wettability? You heard about it? Okay, you're from a very good program. Okay, so let's say there's a surface. Okay, I put a drop of water there. Okay, I'll have this shape. Okay, this is called a contact angle. Okay, now if I actually have the same surface, but I put an oil there, okay, I may get a different contact angle. Okay, or if I actually simply not put the fresh water, I put a fine water, or actually different cooking oil, I may have a different contact angle. Okay, so why is that? Okay, so this is actually the liquid phase, and this is actually the solid phase. I don't know how to use this. Okay, and why is that?
Because the molecules at the surface of the particle of the fluid, they don't have full all angles.
Yeah,
So-
excellent question. Yeah, excellent answer. Yeah, so because there's a surface energy that control the surface tensions, for different surface tensions, you will get a different angle just because different force are actually applied on the surface to allow you to form different shape. Now, this is called wettability and has a lot of applications. Your iPhone is designed to have the wettability so that the liquid won't stick there and won't absorb the water. Okay, if you look at the iPhone, you can drop the material, you see that the water won't penetrate through the screen. Okay, and why is that? Because they actually the magnetic gas or the surface are actually treated to actually form a higher contact area. Okay, so that you won't get wet and enhance the wettability. Now, in general, when we do a multi-phase system, you have to consider this is much harder. In the sense that you have to consider not only the fluid-solid interaction, but the fluid-fluid interaction and the three different combination of interactions. Okay, now then I need to establish the idea of considering that. I'm trying to slowly migrate so I can actually do some calculus. Okay. Okay, so why do I actually need to introduce this thing? Okay, so let me go back a little bit. So what do you learn from mechanics of material? Okay, what is the most basic governing equation of the mechanics of material that you need to know? Is actually the Newton's rules, right? Okay, action equals reaction, so F equals to ma, those kind of thing. Okay, and underlying it, there is something called balance of linear momentum. Okay, what is the form of balance of linear momentum? For solid?
Of
Yeah.
sigma plus the gravity
Yeah, body force. Yeah, okay.
equals to
Very good. Very good. Okay, so how many have seen that before? Okay, so that's good. If not, that's fine. I'm going to explain it. So what is this triangle mean? Okay, it's actually mean divergence. What is the divergence? Okay, well, what is the divergence mean? The divergence. What is the physical meaning of divergence? I just want to ask so that it creates some physical meaning. Okay, let's imagine that I have this surface. Okay, just introduce a 3D surface, and then I consider a point on that 3D surface. Okay, so far so good. Okay, and then I actually bedaub it a little bit, so I form a very small triangle. Sorry, not triangle, square. Okay, and I want to align the square so that it's on the tangent. Do you know what does it mean by on the tangents? It means it's a general. So if I have a curve in 1D, this is the tangent. Okay, it means that it touches upon, and then the surface, the orientation of the surface is aligned with the change locally. Okay, now if I extend it to multiple dimensions, this same concept still apply. And then if I actually obtain this triangle or this square or whatever, so how do you represent the square mathematically? Just go back to your calculus. Okay, so this calculus, this circle, this square will have two orthogonal bases, isn't it? Okay, they're 90 degrees separated apart in 2D in a 3D curve. And what is this? It would be the gradient term, right? Isn't it? Okay, so okay. So what is the divergence? Yeah, exactly. So what does that mean? Yeah, it's just the sum of it, right? Okay, because you have the diagonal term and then you add it together and then you get the sum. Okay, so this actually gives you the sense of the balance law. Okay, now if this is actually considered the material in one phases. Okay, if I have two phases, okay, so and then I have two material and I actually want to perform the calculus on the mixture or material. I need to able to consider the trajectory of both the solid and the fluid. Okay, and not explicitly, but in some sense, this would be the starting point. So what we actually need to do is to prepare ourselves to perform the calculus. Okay, so this is what I'm trying to moving from the mixture theory, special calculus, so to the very general calculus that you learn from the high school and college. Okay, so we need to reintroduce this term now in terms of the solid and the fluid phase because they don't move together. Okay. So by the way, does anyone remember what is the divergence theorem? Yeah, okay, that's really good. Okay, it's already okay. So the divergence theorem say that okay, if I have a functions and then I take the normal vector n, yes, that would be equal to the divergence of the same functions on the volume. Okay. Now, why do I actually want to point out the divergence theorem? Yeah, exactly. So this is the balance law. If you see the divergence term, if I actually take the area, if I take the volume integrations, I'll get back this term. Okay, so this is actually from the finite class. This is actually the balance of linear momentum integrate in the integrate form. So this is called the local form, and this one, if you write it out, it would be the global form. Now, why do I need to care about it? Because I also need to rethink what is the surface area. Okay, so let me explain this. Okay, so let's consider a cubic. Okay, from a let's have a pause media. Imagine there's an orange and I cut a perfect cubic there. Okay, you will see there are some solid tissues. Okay, and then there's some fluid. Okay, so the first question is that is the volume fraction and the area fractions identical?
Area fraction, we have different area fractions.
Yeah, exactly. They're not identical. In general, they're not identical. Okay. However, if you have a random media and then you consider it sufficiently large, then what should we do? We will consider them identical, but it's a big approximation. Okay, so I can give you what you say is absolutely right. Consider that 2D material. If I have the voice, it actually look like this. Okay, this area, that's area fractions would have a very high area volume fraction of air. Okay, this one will be very low. Okay, if you take the average, you get you kind of get the average area, but because you are consider the left area and right area, it doesn't make sense to consider the average. The average will become the volume. So in general, they are not identical. Okay, however, we will again using the assumption that they're identical to make the formulation easier. So, but this is actually a very important point. Now, consider in the case where I would actually still have my indicator functions. that are actually in that with this property, and then I have DAS, and then DAS, and then DA S, and then the whole thing would be dV. Okay, so the portion of the area of the specific phase would be related to the indicator functions times the area. Okay, and dA is a small scale area increment that are much smaller than the global area. Okay, so now in this case, what we can do is the following. If I define the area fractions as this with this label, then the area of the phase divided by the total area will be equal to this. Now this is actually called the area fractions of alpha phase. Okay, and then you can also see the property. Okay, so far so good. Now we'll make a big assumptions, and I guess one thing that is easy to see is that if I take the average, integrating this over the area divided by area, if I actually introduce, sorry. So why don't we do the following? If my battery is out, I'll take a 10 minutes break, and then we can take a 10 minutes break together. Sorry, not just me, everyone obviously. And then we come back. Okay, I use the remaining 10% to teach, to go through as much as we can, because I think I will see whether I can, in the next lecture, I'll see whether I can allocate a better lecture room. I think, is that okay for everyone? I'm not saying this is bad. I mean, I think I like this classroom, but I think that I would like to see whether I can connect this to the screen so that you don't have to, so that you can look into the screen which is facing me and then not just look at your computer screen. Okay. Okay, so this is actually equals to if I actually integrating this along the whole line, okay, so what is x1? Okay, so this is actually dA. So this is actually the dA area. If I actually integrate along the x1 line, I will actually get this term, and that will be the porosity. Okay. So far so good. Okay, just like the point, just like this figure, this would be the x1. Okay. Now in general, so the area volume area fractions is not necessarily equal to the solid phase area. Okay. So, but most likely we will just assume they are actually close to each other. Okay, just to make the formulation easier. Okay, so far so good. This is actually pretty intuitive and doesn't require any domain knowledge. I just need to define a more formal term. Okay, you are still with me? Okay. Okay, so what should we do next? Now I define the spatial thing. Okay, what I want to do is to define the governing equations for the porous media. Okay, and then the pore mechanics part is actually the first version is complete, and then we go to the computations. Okay, so in this class we have the porous theory, computation. So this is the theory portions. So what should we do next? Okay, the material, what is the feature of water? Water is moving, right? Okay, I mean, water can be hydrostatic, but most likely we are interested in the part of the material that are actually moving, okay? So in order to capture that, we need to capture the change. And what is the tools to capture the change? Derivative. Okay, thank you. Thank you. It's obvious. Okay, but I will say the following. Okay, you capture the change using derivative or gradient or divergence. This is true. For that case, you cannot capture the change using a derivative. And what are those cases? When you have jump, you don't have derivative. So when you say, yeah, exactly. When you say derivative, yeah, you are assuming some level of smoothness so that the derivative is actually well defined. Okay. So for example, if you want to define the election, so you can either elect different candidate, but there's no gradient of a Trump or Biden. Okay. Okay, so just because this is in that case you have a setting, okay, or maybe an order set or something else, but you don't really have a smooth domain for you to define stuff, including derivative. Okay, now why do I want to talk about the derivative? It seems very trivial, right? Now, I just want to talk about that because that is actually where things start to become more complicated. For a fluid, for a single solid material, we have something called density. Okay, so what is the density? Density, what is the definition of density? Okay, now there's one mass and one volume, right? Okay, what if you have multiple mass and multiple volume? Which density are we talking about? Now, this starts to become very ambiguous. Okay, because I can have ms divided by v. Okay, that will give me one kind of density. I'll have a ms divided by vs, which would give me another density, and they're not identical, obviously. And I can have a mf divided by vf, and I have mf divided by v. Okay, the four of them. Okay, so the problem of this is that sometimes people confuse about this. And in solid mechanics class, if you pass the solid mechanics class, the first two lectures is just to figure out which density is which. Although I think we should have a more rigorous terminology. Okay, so but we're actually going to define it. Now, this is actually the basic. How do they change? Okay, so this is also difference. Okay. Okay, this is actually why we care about that. Let's just review what is the derivative. Okay. Now, for the post media, I would introduce two different concepts that also happen in computational mechanics. So there's something called local derivative, and there's something called material derivative. Okay. So why is that there too?
Because we have two different Euler Lagrange.
Yeah, exactly. We have a different perspective. Okay.
So if we observe the traveling of, for example, the fluid, then we have the Euler theory.
Yeah, exactly.
Not the Lagrange theory, and if we observe only a certain point, then we have the other one.
Yeah, exactly. Okay. So let me explain that one more time. Okay, I'm sure it could be boring sometimes, but now imagine that you have a window. Okay, and that window is fixed in the space. Okay, and then there's a bird flying through that window. Okay, you can see the bird flying from this side to the other side, and then it vanishes. Okay, so if you focus at one point and you observe the change throughout when the bird is flying away, this is actually what we say an audience feedback. We just consider what happened here. We don't chase the bird, and we don't move our head to chase the bird about what's going on. Okay, this is actually the local derivative, which is actually related to the following. Now, if you think about it in terms of the density, I would define the density as something that I think my computer is going to die of. So I would, oh yeah, actually that's the benefit of not projecting the. Now I can actually charge my computer. Does anyone have a chart? Yeah. Oh, this is actually, you already have this. I don't have to. Yeah, thank you so much. Oh, but I need the, what is that? Oh, yeah. Well,
Oh, wait, no, it's not.
oh, okay, okay. Is there any? Otherwise, I can send the, I think.
You just pull it off my laptop.
Oh, yeah, yeah, thank you. Thank you. Thank you. Yeah, thank you. Thank you so much. Yeah. Okay, I think that's great. Yeah, thank you so much. So, okay, so let's get back to this. So we have a point here, okay. But one thing that we need to think about is that the density itself is a function of space and time. Okay, does that make sense? I'm looking at that window, and then there could be 10 birds flying through that pond or no. Okay, so things are changing. Okay, if I look at different pond, of course I will have a different density of birds flying through. Okay, but I would have this density. Now, how to keep track of the change in time? For that window, I would actually simply saying that I want to actually limit the delta t, pushing it to 0, and then I'm going to just preserve it in the space. Okay, does that make sense? Okay, so what is the calculus definition of this? Is that this is the partial derivative of time. Okay, get it? Okay, because I don't really have any spatial definitions. Now, another one is the following. Let's see, this time I'm following the bird. Okay, let's see what happened. The bird experience. Okay, so what should I do? I would need to introduce a concept where I'm trying to follow the bird itself. Okay, I need to introduce something called a mapping. Okay, so imagine that I want to introduce a mapping that actually for each given a point in the reference point, I will map it to the new positions. Okay, so this is actually called a mapping. Okay, and this X is for reference configurations, reference field, and T is time. Okay. And X is actually called the current time, current positions. Okay, so far so good. Okay, what is the property of that mapping? Now, let's say I have a collection of points that are actually called, that can be any position within this domain, and I will call it dv0, which is actually called a reference. And I'm going to map it. I will introduce a mathematical equations that can map it into a new shape, which is something like this. This is X. Okay. Now, okay, can you give an example of this? Okay, let's say I have a straight line. Okay, so this is X equal to 0. This is X equal to 1. Okay, I want to bend it. This is 1D. Okay, just one dimensions. I want to bend it into a circle. So what would be the equations? So how do you come up with the equations? Very What is your thought process of finding the circle? Just curious. Actually, I forgot the answer, so I have to think about the answer. So, okay, how will you do it? Yeah, you can get some intuition there because this point is not moving. Okay, you see what I mean? Okay, so maybe I would change the problem a little bit. X minus 1, x equal to 0, just to make life easier. Okay, so this point is not moving. Okay, what happens with this point and this point? It will move, right? Okay, what will be the radius? How do you find the radius of the circle? What is the radius? Because you know the circumference is 2. Okay, so anyway, so maybe I don't want to do the calculus here just to finish the course because it's a sign up. Okay, but this give you example how to find the equations. Let's give another example that is easier. Let's say I just have a bar that is 0, x equal to 0, and x equal to 1. I want to make it twice as large as before. Okay, so what should I do? Twice as long as before. What would be the deformation mapping? Yeah, simply this, right? Okay, and everything become bigger. Okay. Now, if I introduce a y-axis, and I want the y-axis doesn't change, then what would that be? Then maybe okay, maybe I don't use. Maybe I use x1 and x2 to be the two coordinate. Okay, if I want to make it longer, but then the vertical position I don't want to change anything. Then what would that be? So
x2 would be equal to x2.
exactly. Okay. So you know. Okay. So this is called deformation mapping. Okay. What is the interesting property of deformation mapping? Is that if there is no factor or anything, you're assuming that the inverse also exists. Okay, what does that mean? It means that if you have a point here, you can find a point here that are 1 to 1. On the other hand, you can find a point here, you can also map it here. Okay, now, unfortunately, the physical world is very cool. So, okay, sometimes you're violating that, and what is the possibility or how do you violate that? For water, obviously, if you have fluid mechanics problem, you never consider this. But if you work on solid, okay, sometimes the inverse doesn't exist. What happened in those cases? Why? Okay, so that's the issue about this paper, and I do this.
You just break it.
Okay, I break it into two, right? Okay, so what happened? Okay, I would have mapping, but then the inverse doesn't exist simply because I would actually introduce a jump in the displacement. Okay, so if we introduce a jump, that means I will have the smoothness is break down, and I have you know what I'm saying? Why is it there's a displacement jump? Because previously the whole thing is attached. Okay, so at least I see zero continuous, but now it's separate. Okay, so there's a jump. If you want to describe that kinematic motions, okay, suddenly the displacement come from 0 to 1 on the crack line or whatever. Okay, so this is actually an assumption that may or may not be true, but we will assume that this is true. Okay, what are the other examples it could be violated? Okay, imagine you have something have finite volume and suddenly collapse into a pond like a black hole or whatever. Okay, so which could happen. Okay, so do you have 1 to 1? Obviously, you don't have 1 to 1 because the finite volume collapse into a single point. It's a singularity. Okay, so that's it. So anything with singularity would actually violating that. And what are the other property of this deformation mapping you want? Sorry, this is a deformation mapping, but what if I actually take a derivative of it? What would that measure? So if I take a derivative of it against the x, I will get something called deformation gradient. Okay, and what would be that gradient? The gradient is also a tangent surface in the deformation mapping. But what would be that deformation gradient?
It's the stretching.
Yeah, exactly. Okay, this is actually great. This is kind of like a strength, but in a finite deformations setting, you're really considering the mapping. Yeah, but they tell you what is the change between that. You see, this one is actually, if I take a derivative, then what do I get? What is the f? If I take a derivative, this will be just 2, 0, I'm sorry, 2, 1, 0, 0. Okay, you see what I mean? Okay, so there's no shear. You can see there's no off diagonal. Okay, so now what is the property? What is also another necessary property is that the derivative of f is actually have to be greater than 0. Okay, does that make sense? Okay, you can change the volume, but you cannot change the volume to a negative volume. Okay, you see what I mean? So you can have photon, it can collapse as small as you want, but not collapse into a point, but you cannot flip the other side. Okay, if you do that, you understand what I'm saying? Okay, so why do I actually introducing that mapping? Turn out that if you want to follow the material, you have to deal with the fact that the material is moving with that deformation mapping, right? So you actually need to introduce the calculus according to that. Okay, so what would be the thing that you need to consider is that you would actually need to consider what happened to the density that actually are now written not just as the small x in the current configuration, but this. Okay, so the coordinate system that you consider if you want to follow the material is itself not fixed. It's actually changed over time. Okay, so because you want to follow the material. I think this is actually very common in fluid mechanics. If you have fluid mechanics background, you see that. How many of you already taken a fluid mechanics course? Okay, so you probably already know. Okay, it leads to a local term and a convection term. If you do that, I will take a time derivative of it again, and then what I would get is still the partial term, but I will get a second term, which coming from taking the partial derivative of this over time. Okay, and what would that be? Okay, so this is actually the local term, and this is actually called the, what is the name of it? This would be the convection term, right? Okay. Okay, and let me using the calculus terminology. I like to write triangle, so that would be this. Okay, or more likely, people like to write it as this. Okay, this is actually not the volume, but velocity. Okay, so what is the difference between speed and velocity? English what? Language what? Yeah, actually, velocity is actually a vector always. Speed is usually the measure of that vector, which is actually usually a scale. Okay, so far so good. Okay, and then I would actually write out all the possible way to write the same thing, just to be sure. Then I would also write gradient of dot v. Okay, that grad is not graduate school, but the gradient is the short term for gradient. And just writing, you can write in triangle, you can actually write out the term, but it's actually okay. So far so good. You think it's a good time to take a break? Okay, maybe take a break and then we come back at 11:57, 10 minutes from now. Thank you. how's the research going?
Well, actually, I didn't. To implement the transverse isotropic model in the phase field, I had to change the whole formulation for the phase field. I mean, to change the split, but I can show you how. So this is how it looks like. So basically, those are the 4 different experiments that they perform for the same geometry. This is the center nodes, which is not mode 1 track. And I calibrated everything based on this experiment. This is the off-center.
You just use the regional factor model.
Yeah, but with the single material parameter for the fracture toughness and the linear isotropic material, linear elastic isotropic material. So yeah, here in this one, where the mode 3 also has a contribution, the curve is far from the. But also there is some discrepancy here. I don't understand why this happens in the measurement.
Whether we can. Do you work with champion on the inverse problem? This is just on inversing with the.
No, I didn't.
The loading, but without the spatial pattern.
Well, the crack path is very simple for this 2K, so yeah, I'm getting the crack path, and
So what do you think would be the next step?
I don't know. Actually, right now I'm just changing the code to so I can run it on the GPU, because I have to change some stuff to run the iterative solver, because everything here is with direct solver, so I'm not using many elements, so I have to change the structure of the code.
Okay. I'm guessing that. After this lecture, I'll see whether I can try to reserve the. I'll see whether I can try to reserve my. To see whether I can reserve the room for the in the 7th floor, so we don't have to come here. But if not, then we assume we come here. And also today I'm a little bit rushed, so I haven't print out the syllabus. I'm going to post the syllabus in the coursework after the lecture. I apologize for that. I just don't want to come to the office to have another 10-minute delay. Then okay. So, but next time I learn the lesson, or I try to avoid it. I try to avoid other people have air charge, have a car accident or something. I don't know. So yeah, but I can come a little bit earlier. So it's always a interesting way to commute from New Jersey to New York. Because you can come here with the free parking in the general grants too, but then they have different hours. If you actually park in the wrong hour, you get a gigantic ticket. Or you can actually have the daily parking outside the city and then take a train to the subway. Anyway, so that's my issue. So are you guys all from civil engineering or you're from? Huh? Oh, Earth and Environment. Okay. Who is your advisor? Oh, okay, okay. I see, I see. Okay, I think we okay. So okay, so we'll talk about that time derivative. Okay. So far so good about the density. Now we want to generalizing this concept not to apply to density, but the general discussions on the material time derivative. Okay. By the way, let's consider generic functions f as a functions of as a function of time, and that this is actually integrating it over a domain. Now, this is not the area volume area fractions, but just a general functions that are generic. Okay. Now, let's imagine something that are fully saturated. So, okay. So in the undergraduate class, you probably have this CSR or S item that indicate that the degree of saturations. For in the class geomechanics or geotechnical engineering terminology, the degree of saturations equals to 100, meaning that all the fluid are actually water in the pore space. Okay, which is actually generally what happens. So you can imagine something that is submerged or below the water table as a material that are fully saturated. In this case, at time t, we have a Vt. Okay, so this is the volume at time t. Okay. Now, if you observe it after a while, I have this new shape, and then there's a really volume of t times delta t. Okay, does that make sense? So we're changing it gradually, continuously, nothing suddenly happens. And then in this case, if I actually basically derivative doesn't make sense if you have a jump. Okay, so just a friendly reminder. Okay, so and then I would actually consider this as a derivative that looks like this. There are also another very popular terminology is that people use capital letter to indicate the material derivative. Okay, so I'm just indicate integrations. Now, there's one important note that I want to emphasize, and that are actually often is a violation that often committed, and that would be generally speaking, this could happen. Okay. So you take the total time derivative of a function's f, and they are not equal to the density function taking the derivative and you integrate it over the volume. Okay, so do you see that? So I'm saying that this is actually generic functions. This is the corresponding density functions. Why do I call it the density functions? Because it's something that actually inside the integration of volume, right? Okay, so I'll give you an example. If this function is mass, this one will be density. So that's why it's called density functions. Okay, but there are other density functions like power density. So what is power density? If you integrate power density function, what do you get? You get power. Okay. If you actually have moment density, then you integrate more volume, you get back the moment, okay, or the momentum, okay, accordingly. Okay. Now, in general, if you take the time derivative and integrate over the volume, it's not the same as this whole thing integrate with the volume and take the time derivative. Okay. So the order doesn't matter. And why is that? Why is that? Huh? No, it's not because of discontinued. Okay, just think it intuitively. Why is that? Because, okay, you probably know the answer, I think.
It's a relation of mass. It's not always.
Yes. Well, I mean, you can argue that the mass is always conserved in a Newtonian sense, but what happened here is something is the following. Yeah, in some sense, you're also right. I mean, you're not capturing the same dV. The film itself is not fixed; it's changed over time, like here. Okay, so the dV is not a constant. Okay, it's in the current configuration dV, not the reference one. I'm not integrating over dV. Oh, that are the reference. I'm integrating over dV. And from the time from t to delta t, the configuration is changing, right? So the meaning of the derivative on the tangential flow chasing the material is changing over the time. Okay, so the order actually matter a lot. Okay. Yeah, if you don't want it to be exact, everything is similar. And then, but I would say that sometimes people make that mistake and publish it. Yeah, I have seen that. So I actually have put it in record, but anyway, if it's true, I guess nobody can say anything. Yeah, but this is actually very important. Okay, so basically, I would be learning this integration term. And you may wonder why I did not do anything in local term, but I did everything in integration term. And that is actually because later on you will see that I need to consider the integral because it's in some sense. In some sense, it's more intuitive to consider the integrations because I can easily extend to the multi-constituent, multi-phase material. Okay. Okay, so I have these relationships. And then if I actually take out the first term, that are the partial derivative, okay, what would be the second term? Okay. The second term would be the convection term, right? Okay, what would be the convection term look like? Okay, it will be actually on the change of the t term, and then if I actually apply the divergence theorem, so this term will give us the velocity times delta t dot n times dA equals to dV. So what is n? n is a normal vector. So I have a volume, and then n is the vector that pointing outward. That would be the n vector. Okay, so if I actually substituting this back, what I would have is that I will keep the first term. What I would have is actually the limit of delta t equal to 0, 1 divided by delta t times this. So, then I would actually eventually what I will have is that the total functions would be equals to the local term times the divergence of this density function times the velocity. Okay, so far so good. Actually, I skip a few time steps there, but and what is that? So I can cancel this out first, okay? And then the second step I did is that I play around with this. I apply the divergence theorem so that I get back to these equations. Now, I haven't given it a particular name, but if this one become the density functions, then I simply would have one of the conservation principle, and that would be balance of mass, right? Okay, because I know that m dot mass is not changing. Okay, I'm not talking about Boss meeting right now. You can have it's a co-system. In a co-system, there's no mass created or destroyed. And what I would have is that the change of the density over time is actually equal to the divergence of the density times the velocity, which sometimes called the mass drop. And this one would be the conservations of mass. Okay, so far so good. You take the local derivative as the divergence of the rho times v. Okay. Basically, can you see that? Can you see what is the meaning of the equation? I think that's important. You see this term is spatial, okay, and then related to the velocity. And this one is actually temporal. There's a time derivative. So imagine there's a box. What happens with the change of the box is related to what come in and what come out. Okay. You can only change the amount of the matter in that box when you're actually pulling things in and out. And then you have to consider the derivative because in a box there's 6 different phases, right? The opposite phase and the sum of the change of that box of the boundary actually will affect the bulk volume. Okay, so far so good. Now, does any of you have fluid mechanics major? Okay, so I think it's fine. Okay, so now this is the balance of mass of a genetic material. Okay, what if the material is incompressible? Okay, what is the characteristic of so what if the fluid is incompressible? Or the material is more generically, material is incompressible. Okay. What is the definitions of being incompressible?
No volume change.
No volume change. Okay. So what happens if a material doesn't have volume change? What happens to the density?
Doesn't change.
Density cannot change. So how can I rewrite this?
First time is 0.
Okay. So first term is 0. So I will get back this. Okay. What else?
You can take the density out
We can take the density out. Why?
because it's a constant.
Because it's constant. Why is it constant?
It doesn't change.
It's incompressible. Okay, that's good. Yeah, sometimes you have to. I learned it from the citizenship test. You have to ask the same thing in multiple different ways to see whether someone is lying or really understand something. Okay, so if we take it out, then what we have is a beautiful thing just divergence of velocity equal to 0. Okay, then you will see that this, in fact, this constraint happen a lot in most in a lot of governing equations. Okay. Okay, so basically the divergence, basically we call it the velocity is divergent free. Okay, so divergence is pretty much related. You rewrite a balance of something, it always involves a divergence. Okay, because at the end of the day, you want to see in a matter whether the change in all the different orthogonal directions sum up actually preserve something. Okay. Okay, so okay, does that make sense? Okay, what are the different ways to say divergence v equal to 0? Okay, there are also different ways to say that. Okay, so let me visit that a little bit. Just remind the undergraduate your undergraduate experience. Let's consider cubic. Okay, and then the dx1, dx2, dx3. Okay, together they form the volume dv equals dx1 times dx2 times dx3. Okay, this is the volume. Okay, if I take the, if we become divergence free, what am I saying? Okay, I'm simply saying that I'm simply saying dv1 x1 plus dv2 x2 2 plus dv3 x3 equal to 0. Okay. So from your undergraduate course, what is the other name of partial derivative of v corresponding to x1? Partial derivative. What is this? Okay. So now let me talk about what is this. This is the string. Okay. I hope you still remember what is the string. What is the definition of the string? It's actually 1/2 of the gradient of the displacement plus the symmetric term of it. Okay, the transport of it. Okay. Now, what is the rate of change of the deformation? What is of the string? Okay. Now, in the small deformations regions, we will call it V. Okay. Now, what is this? What is this term? Now, let me write it in matrix. Okay. So this is just V1, X1, V2, X2, V3, X3. What is this term? Or X2? 2, yeah. V1, X. Okay. Should I write more? Yes. It's symmetric. Why is this symmetric? Okay, so let me do the following. Let's say I have a matrix A, and I have a matrix A transpose. Okay, if I make a transpose of A, what happens? I will have the A transpose plus A transpose, which give me back A, which is actually the same. Okay, so it's symmetric always because by deformations. Okay, so what is this equations?
It's a trace of
Yeah, exactly. This trace just add the diagonal term together. Okay, so far so good. Okay. So for solid mechanics, the balance of mass for incompressible material simply imply that the trace of the epsilon dot are equal to 0 for incompressible material. Okay, for solid mechanics, it's actually pretty easy. But well, I mean, from a theoretical point of view, it's easy. From the implementation point of view, in file element, it's difficult because you have to put it either as a penalty or as a Lagrange multiplier. okay, which is actually create another type of difficulty. And if you take a fundamental course, you will encounter something called locking. Locking is actually basically related to this when you put it in numerics, okay? So for example, these two things fixed, and I have this one element, okay? And I told you the material is incompressible, and now higher force here. What will happen? Or maybe I have higher force here. They're not going to simply, not because physically it's not going to move, simply because your mesh actually create too much constraint for the material to move. Okay. So this could be the problem of the material. Now, this is one way to think about it, the incompressible material. There's another way. Now, you can write the current deformations as the determinant of F divided by dV. Okay, and sometimes you write J dV because J is actually the Jacobian. Okay, so and deformation gradient, as we define, is actually the gradient of the deformation mapping. Okay. Now, what happens to J if the material is incompressible? Incompressible meaning that this volume will be identical because it's incompressible. You don't change the volume. So J is also equal to 1. Okay. Okay. Let me ask another point about important questions. What is the relationship between this and this? They're not identical. I mean, they lead to something identical under different assumptions, but they itself are actually not identical. Okay. In the first case, I actually given the conclusion that the chase of the epsilon dot equal to 0 by assuming that the current and the reference configuration are actually identical, so that I don't distinguish the gradient. Okay, the gradient is actually, if it's more precise, any gradient or divergence has to be associated with the frame. Okay, if you say gradient without giving it a coordinate system, it has no physical meaning. Okay. Now this frame is actually changing, but we ignore that. Then we will get divergence of epsilon dot equals to 0. If you don't, then you get the Jacobian equals to 1, and they're not identical, but they're related. Okay, so we can talk about it later, but I don't want to make it become a math class. Okay, it's related. They're related because one is in the multiplicative group, and another one is related to the corresponding Lie algebra. Okay, so I won't talk about the Lie algebra here, but in the future, you would actually probably encounter that. Okay. So far, so good. I think we introduced the balance of mass, which is actually one half of the course. So, okay, so the course only have two, actually 1/3 of the course. Okay, so how many balance principles do we have? Okay, in physics, balance of angular momentum, balance of linear momentum, balance of mass, balance of energy. Okay, you have thermodynamics inequality, but if I don't use inequality to be the constraint, then I have at least these 4 equations. Okay, so I think I cover 1/4 of it. Okay, so anyway, so far so good. Now, the idea is that how do we extend it to false media? Okay, so what I actually did is supposed to be the review. So if you find it anything new, that is fine. Okay, I'm also trying to make it self-condensed. But here is actually what is actually the new part. Okay, which is actually put it at the yeah. So false media or poromechanics. Now, I'm going to redo what we did, but this time I consider two-phase material, okay? Assume two-phase. Okay, so the integrated function is either solid or either fluid, and they equal to 1. There's no air or any other outside. There's only one fluid phase. Okay, so far so good. Are you still with me? Okay, now I consider the two-phase material. Okay, now this is at T. Now after a while, what will happen? Now, strictly speaking, I will have a solid trajectory that map to all the reference point to this. And then I would actually have this thing deformed, and I have a new configurations. So far, so good. Okay, so what happened to the water? Let's use the yellow part to do the water. Okay, are they following the solid trajectory? It's possible if you have an orange or whatever. You can argue that because the scheme is actually impermeable, roughly speaking, and then you deform it, the water is still trapped in there. But in general, you don't make that assumption. So instead, what do you have? Instead, you would have another mapping and map the fluid into something, into new configurations. What would that configuration look like? It may occupy some part of the space, right? Of the fluid, of the solid, but they may not occupy the whole thing. Okay, now, then what happened to this part? Where are the fluid come from? It's still fully saturated, right? So, okay, S remain 100. So, where is that water coming from?
Adjacent space.
Yeah, from the adjacent space. Okay, so this is very important. So, here, you actually, in this case, when I say what the water coming from, I'm viewing it from the solids perspective. I'm following the trajectory of the solid, which means that I take this as a predominant configurations, and then I'm actually consider the relative movement of the solid from the fluid, so that I'm saying that this part where the material that are outside the domain are actually there will be part of the water that are moved in a different way than the solid, so that it doesn't map into the current configuration of the solid. And this is compensated by the water that are coming in. Does that make sense? Okay, so now what happens if the water is incompressible? So what happens if the green area, what is the size of the green area relative to the white area if the material is incompressible? It will be the same, right? Okay, so it's actually okay, but then the important thing is that inside of one mapping, you have two mapping. And if you actually want to define a material derivative, you have two material derivatives to consider. Okay, so in geotechnical engineering, mostly you follow the solid trajectory just for convenience, because you will need to write a material model in the solid, but sometimes you may want to use a fluid, depends on what you want. Okay. Now, but what happened to that is that now I don't necessarily only have one material time derivative, I have two material time derivatives. Okay, first I follow the solid part of whatever's alpha. Alpha is just a term for the physical quality, and then I will have the local term plus the gradient term times the Vs. Okay, so this is actually the first term is a local term, the second term is a convection term. Now this Vs is only for the solid, okay, not including the fluid, not the mixture. There's a special case where the fluid and solid have to follow the same trajectory, and this is called the undrained case. in your undergraduate solid mechanics, you may heard undrain. What is undrain is that you don't allow water to coming in and out so that they trap together. If they trap together, they are going to drain, and then the two trajectory will collapse into one. Now, if the same physical quality is actually followed by the fluid, then we will have these equations. Now, they look almost identical, right? What are the difference here? Just this F term, and this F term, and this S term, and this S term. Okay. So far, so good. Okay, so okay, so now what would we want to, how would we want to divide the balance of mass or balance for the fluid and solid? Does that actually impose any change from before? Do you change anything? So what would be the time derivative of the solid mass? So the balance law for balance of mass for solid. What would that be? It would be still the same, right? I mean, I'm following the trajectory, right? So how should I write it? I would substitute alpha, which is a transport quality, into something else. What would that be? That would become the solid density, right? Does that make sense? Now, but then the important thing is that what density is it? Yeah, there are multiple solid density. Okay, so now let me write it out. So now I will define these two density. Okay. What is the difference between the two? This is the volume fractions of solid, and this one is actually the solid density one. This is the solid density 2. So how are they related? Okay, in your undergraduate course, you may learn something called specific gravity. Okay. What is a specific gravity give you? Is a relationship between the water density and the solid density, and that density is the intrinsic density. What is the meaning of the intrinsic density? Is that is the ms divided by vs. Okay. Now, what is these two density? The first density is actually the intrinsic density. Okay. The second one is actually the partial density. Okay. So now let me write down the equation. This one is related to Vs, will be divided by V. Okay, the total volume. So rho S is actually rho under rho subscript S is actually related to the ms divided by Vs. Okay. So now the partial density is actually related to the volume fraction of the solid times the intrinsic density, which is actually, if I write it out, that would be ms divided by vs here, and this one will be vs divided by v. So what we have is actually ms divided by v. Okay, does that make sense? Okay. So now go back to these equations. Which density should I use? Huh? Yeah. Well, why is that? That's a very good guess. Why is that?
Like part of it that's made up part of it. So let's solve it.
Yeah, it's more convenient, right? You see what I mean?
Space. Yeah.
Because consider the surface area. Okay. Do I actually want to actually explicitly consider all the area, or do I just want to consider this? Okay. So I can take advantage of the assumption that I'm assuming that the area fractions and then the volume fractions are identical, and I just can simplify my equation. So I write this. And that's it. And I would just spread it into two terms. Okay, the same thing for the fluid. Okay, so far so good. Okay. Now, let me write it out. Okay. If I write it out, then I will have this. Okay. So do you see any opportunity to further simplifying it? Okay, so in your undergraduate solid mechanics, what are the other assumptions you make is that the solid itself, the grain itself is incompressible. Okay, the soil skeleton itself could be compressible, but the individual grain is incompressible. Do you know the difference between the two? Okay, I imagine that I have some marbles, what is that for marble ball or whatever. So I actually assemble this structure. Okay, the marble itself is supposed to be incompressible. It's not exactly incompressible, but I can easily collapsing them into something in a more compact state. Okay, so if I look at the skeleton is getting smaller. Okay, but then the individual particle, they are actually incompressible. Okay, so what happened is that the partial density of the solid is changing, but then the intrinsic density is fixed. Okay, does that make sense? Okay, so what happened to this is that I'm going to take rho s out because rho s is not going to change, and assuming that this is actually homogeneous, then what I will left is just these equations. Okay, does that make sense? Now, if you have two material, be aware of that gradient. Okay, with two material, what happens is that or you have a density of the intrinsic solid that are not constant, you would actually rise another term. Okay. Okay, so what happened to the fluid? Okay, it's the same. Actually, I need to put a little bit of acid. Okay, so now I'm just want to write a gradient s corresponding to the trajectory of the solid. This is one is for the fluid. Okay. So far so good. Okay, I'm going to do one more thing. What if I add these two equations together? Okay, what would be the local term of like this one? It's zero, right? Why is that? Yeah, the volume fractions. If you consider the summation of them, they always equal to one. The gradient. Okay. Okay, that looks better, right? Do you think so? So how do I further simplify it? Can I further simplify it? There are opportunities to do that. Okay. First, sorry. This is 1 minus theta f, right? Okay, so far so good. And then what? Let me write it out first. Let me take care of this gradient of s dot ds. Okay, so this is a 1 term minus the gradient of okay, so far so good. Okay, what should I do next? Yeah. So what should I do next? At 4 minutes. So what is the definition of Darcy's velocity? Do you still remember? Or the relative velocity? Now here, notice that I have two gradient operator s and f. Okay, and then the two gradient are actually different, right? Okay. Now, and then there is also another thing, vs and vf. Okay. Now, I will give the answer in the next lecture, so you have something to think about. But in general, in the mechanical support media, okay, you are not necessarily calculating the VF because you don't know what is the absolute velocity, but you know the relative velocity. What is that? What is the definitions of the Darcy's velocity? Okay, let me do the following. Sorry, it's not the test of the sorry mechanics course. Okay, let me first define what is relative velocity. Relative velocity is the change of the Vf minus Vs. Okay, so sometimes people do this. Okay, why do we care about that? Because of the trajectory. Okay, so I'm actually not necessarily need to model reconstruct the entire trajectory of the fluid mechanics part. I just need to map it to the solid thing first, and then I know the relative change between the solid and the fluid, and then I can directly capture the fluid, right? Does that make sense? So I just need to first think about this current configuration first in the fluid with the solid fluid, and then I reconstruct the fluid motion from the relative velocity. Okay. Now, and then this is the relative velocity, and then there's a Darcy's velocity, and they're not identical. What is Darcy's velocity? It's actually rho f theta f. Okay, so this is actually Darcy's velocity. Why do you define the Darcy's velocity this way? It's simply because, like the mass, we want to avoid to directly calculate the intrinsic volume, velocity, and then using the more convenient effective area. Okay, why do I say that? Imagine that I have force media, and then I have a few holes there, and then the water is passing through. Okay, okay, so far so good. Okay, so now if I actually want to compute the true velocity, I would have to keep track of all the velocity locally and do area integrations, right? And then I take the divided by area, and I will get the average velocity of the phase, right? Is it easy? It's pretty complicated, right? Okay, so why don't I do this? The following: I just measure how many mass in and how many mass out, how many mass that are coming out. If the material is incompressible, then I would actually have the idea of how many mass that are coming out, right? If I actually relate it from the density, I'll get a volume that are coming in. Okay, the volume divided by the volume change in time divided by the total area will give us the Darcy's velocity. Okay, do you get what I'm saying? Okay, this is actually because the true area is actually the true area of the fluid is actually related to the volume fractions of the fluid times A. Okay, so this porosity term is coming from this. Okay, it's related to Harry Darcy when he divided the falling head and constant head divides that what they can measure is just the mass that are coming out, not the intrinsic velocity. Does that make sense? So let's give another analogy. There's a free hole there. What if you have a black hole here, and then there's a velocity, and then the shape is the same. Okay, so what? And then if the mass that are coming in and coming out are actually identical, then do you actually get which one will have a higher intrinsic velocity? If this one m in 1 and m in 2 is equal to each other, and then m out 2 and m to 2 is actually equal to each other, which one would actually have higher intrinsic velocity?
Saying the water hole is way bigger.
Yeah. This one is just a really tiny hole. This one have a one big hole in it, connected all the way. Yeah, the little one have to be moved much faster to compensate by the fact that the area is very small, right? It's like a highway. You can have a 10 lane and then move very slowly. They will still be faster than have one lane and then move very fast, right? Okay. Anyway, so okay, I think I give you a taste of the calculus of the course media. As you can see, a lot of them are based on math. It's kind of boring right now, but it can do a lot of things. Okay, so bear with me. If you can using it to simulate surgery of a tumor, how to removing it, squeezing orange, squeezing sugar from a can, or biomechanics, frozen meat, or whatever, or as well as utility engineering structure, how to build a foundation, why it's settled. We can answer tons of questions that involve water and solid. It's so, but then the fundamental thing is that as you can see, do you think it's easy? I think it's pretty easy, but it's very easy to get confused because of the multiple terminology. Okay, and then a lot of ideas are very close, but they are distinctive. Okay, you know what I'm saying? Density, for example. Okay, so if you forget about anything, make sure you know which density is which derivative is which. So there are two types of derivatives, local and material. They're completely different. And then there's total density, intrinsic velocity, partial velocity, partial density. Okay, so so in this lecture, I'm just formulating the mathematical part. And then next lecture, I will do the finite element part, and I come back to numeric finite element, numerical finite element, and roughly speaking, I try to do that. And then in the next lecture, what I'm going to do is that I'm going to assume the solid skeleton is also completely rigid. Okay, in this case, what problem will you have? Okay, you will have Poisson equation. Okay, so you just need to solve the divergence of the gradient of something equal to 0. Okay, as easy as that. Okay, then later on we relax the idea to make the solid also deformable. That give you the consolidation equations, and then later on we say that there will be free phase, and then later on we add the large deformations, and then we can add the factor, plasticity, and then you just build up from that very simple idea. Okay. Okay, so I think it's a very interesting course because I think all the other courses require you to, I mean, Pro mechanics course is very dear to me because this is the first course that you can just use your brain to study. I mean, if you actually if you study the undergraduate sound mechanics, you have to remember how to do a Casagrande chart procedure, how to draw the phoneme, blah blah. So here, none of that happen. You just need to have a good tools to use your brain to think about the logic and calculus, and that's it. You can divide all the equations. And of course, then if you want to really finish a simulation, you need the constitutive model. This would be another course in the fourth semester. So, okay, so here I'll give you the basic ingredient. Okay, you see what I mean? That are necessary to build a model. And I will introduce very simple constitutive model to allow you to model a bunch of stuff. And then if you want to master the art of modeling the material itself, that will be the course 44. Okay, so the different combined. And then the fourth course would also include the AI. But this one, I think you can include some machine learning stuff. By the way, do you guys prefer to have it or prefer to not have it? To have some machine learning component? Can try. Yeah. Yeah, we can always try and then we still happen. Yeah. But I will try to, but in this course, I'm trying to take care of the fundamental first. And then I will reserve the last few lecture for a more advanced topic. Okay. Yeah, if you have any questions, let me know. Again, there will be no homework. I will post some optional homework, or you can use a PhD level course. So, and then I would actually also lay out the format of the finals. Okay. Now the final, you can ask your advisor, or you can think about some topic that of your interest, and you can let me know. It's very free. Okay. Again, it's a PhD level course. I don't want to really do the how to say the very detailed micromanagement. Just use the time wisely. Then I will try to grade accordingly. The goal is just for you to learn something related to performance media. So one only requirement about the courses project is that it has to be related to performance mechanics, which I think is pretty much easy to find. I would say that the less thing related to performance mechanics than the thing that are related. So okay, so I think that's it. So thank you. So I apologize for the delay or logistic issues. I'll try to fixing that before next week. I'll please check the email about if I can change the lecture room. If not, then we'll meet here. But I'll try to see whether I can fix this computer. Okay, thank you. let's do